Okay, thank you very much. Good afternoon, and thank you for being here. In this talk, I argue for an entity realist account of black holes, which means belief in the existence and certain properties of black holes is justified, even if we remain cautious about theoretical descriptions used to characterize them. And because this talk and the next two talks are all about entity realism and about astrophysics, this can also be understood as a sort of introduction to this part that we have in the conference on the relation between entity realism and astrophysics. An entity realist account of black holes might sound surprising to those of you who are familiar with hacking work. We have just heard hacking, although hacking is one of the founders of entity realism, he was notably he relies on the notion of manipulation, and because of that, he's skeptical about astrophysical entities such as gravitational lenses and black holes. So an entity realist account of black hole might sound surprising. Even Simon Alzen, in a recent work, has extended this problem. He has argued that the same difficulty extends beyond hacking's position, drawing on the views of hacking and also Cartwright and Chakravarti. He concludes that we cannot be both realist about black holes and be entity realists. So his argument can be summarized as follows. According to hacking, only manipulable entities can be considered reliably as real, whereas black holes are not manipulable. We cannot do experiments on black holes. According to Cartwright, an entity exists if it causes the outcomes of experimental tests, whereas the inference from the effect to the cause is theory loaded. And so we use theories and models for this inference, and then we should be also realist about models and theories. And the same problem appears for Chakravarti. Chakravarti supports belief in those properties of entities that are causally connected to our detectors. But the relevant properties of black holes, such as spin and mass, are not detectable in this sense without relying on models and theories. So it sounds there is a dilemma. We should either accept the scientific consensus about black holes, and the assumption is that there is a consensus about at least the existence of black holes, but reject entity realism, or retain entity realism but suspend belief in black holes. And I would like now to ask you, which direction would you like to choose among these two? So first, this one, accept this consensus about black holes but reject entity realism. Okay, so there are a number of people at least. And this one, retain entity realism but suspend belief in black holes. Oh, good.
What about entity realism in black holes?
So it's here.
Okay.
It's here. So that's exactly what. Okay. So that's the plan. In this talk, I try to resolve the dilemma by defending a version of entity realism about black holes, which captures the justification that astrophysicists have for the existence of black holes, and also argue that that scientific consensus concerns the existence of black holes, not the theoretical descriptions of black holes. So I try to make entity realists happy in this way. So the idea of entity realism, first, this is at the corner of my slide. It's the structure of my talk. I start with introduction, then alpha, beta, gamma, and then conclusion. It's somehow is visible there. So I start with introducing the idea of entity realism, then alpha, beta, gamma, and then conclusion. That's the plan. And you will discover what are these alpha, gamma, beta, gamma. So the first ideas of entity realism was originally developed by Hacking, Cartwright, and Geary in 80s. their central claim was that we are justified in being realist about certain entities when we can interact with them experimentally, especially through intervention, manipulation, or experimental testing. Since then, the view has been refined. Various scholars have expanded, clarified, or illustrated the idea or revised it. For example, Shannon Waller shifts the emphasis from actual manipulation to kind of explorability of evidence. Or Matthias Egg here develops a causal account of realism. And Marcus Eronen highlights the importance of evidence and robust evidence and the robustness of evidence. The version of entity realism I support here today builds on these developments. So how? Okay, so I've also contributed to the discussion, and I argue that realism about an entity is justified if it satisfies these three conditions: alpha, beta, and gamma. So this is the structure. Alpha, there must be a well-defined. So and it's based on a causal relation between the entity and empirical results. So in one way, the entity is responsible for the production, causal production of empirical results, and on the other side, we can infer the reality of the entity from empirical results in a form of inference. But there should be three conditions that are satisfied. First, this relation should be well defined. We should know how to manipulate the cause, and how by manipulating, how by changing it, we can see the changes in the effect. So there should be a well-defined notion of what it means to manipulate the cause and see the effects. The empirical results should be robust, reliable empirical results. So we should have different ways of detecting or observing the same thing. And at the end, the real entity that we causally infer from the empirical results should be the only candidate to account for the empirical results. So if there are alternatives, we cannot be very strongly warranted to believe in that entity. And as I said, this framework is indebted to Matthias Egg's framework, but there are some differences. So we can come back to that perhaps later. But most importantly, I build on the notion of robust evidence instead of this empirical adequacy. And here on the non-redundancy or no alternative for our hypothesis, I put more emphasis on societal aspect. And I also discuss the circularity issue here. That's relevant for my argument. So that there are some differences, but we can come back to them. But the general framework are more or less similar. So now we went into alpha. So manipulability is now what we are discussing. And an idea common in recent versions of entity realism is the rejection of the idea that what I'm doing. We are here. Okay. That actual human manipulation is indeed needed for realism. In this respect, James Woodward's interventionist account of causation is particularly helpful. His framework accommodates natural experiments and hypothetical experiment. In natural experiments, processes that have the structure of interventions but occur naturally rather than by human interventions are the main processes, and also hypothetical interventions. We can, when we can, indeed, we know what would happen if a cause were modified, even when the actual modification or intervention is not possible. What we can know how the change in the cause can have some effects on the effect. We know the details of this causal relationship that provides us with a kind of hypothetical intervention. So this emphasis on manipulability instead of manipulation shifts attention from the traditional distinction between observation and experimentation that we can find in hacking in particular. And instead, it shifts the attention toward how empirical results are causally connected to entities or to the target system. So are black holes manipulable? Let's first see what black holes are. We should know what black holes are to know if they are manipulable or not. And the problem is that there are many definitions of black holes. In different subfields of physics, you can find different definitions based on different notions, based on the notion of singularity, causal boundaries, and so on. I do not delve into the details of the definitions in more mathematical or theoretical physics. But what is more relevant to my presentation here is the astrophysical notion of black hole. In astrophysics, black holes are typically understood as compact, highly energetic, no-escape regions of space-time. And they have certain properties like mass, spin, and charge. Indeed, they have these three properties. And importantly, we can compare black holes with different properties with each other. We can compare black holes with different masses, for example. And this gives us a form of manipulability. We can see how changing the mass of a black hole can change observational results. And I argue in this part of the presentation that we have well-defined, scientists have a well-informed understanding of the manipulability of black holes as observational objects. There are different ways of understanding the manipulability of black holes. One of them is hypothetical manipulation, as Dabrowski and Leckhol in this quote points out. One could, in principle, extract energy from black holes through the Penrose process. One could also use a black hole for gravitational maneuvers. So, like using planets to gain energy and to direct spacecrafts, for example. We can use the same thing with black holes, but these are, this shows us that in principle it's possible to use black holes as instruments. So, and we know that the relations, the science behind that. So, in a sense, black holes are manipulable in principle, even if we cannot carry out actual manipulations. Furthermore, nature can perform interventions on black holes. Two important examples are accretion and mergers. In accretion, black holes eat stuff like matters, etc. And in mergers, there are two black holes that are merging with each other, and that's a process. Then first they are separate, but then they merge with each other. Accretion occurs when gas, dust, and stellar material falls into a black hole. This process changes the black hole's mass and can also affect spin. So these changes leave observational traces, and we can observe them as electromagnetic radiation emitted by that accretion disk. There's a disk called accretion disk when black holes is eating stuff. And mergers provide an even more striking example. When two black holes merge, the resulting object differ in mass because there are two black holes or one black hole and one neutron star, and they merge with each other. So the result has more mass. Obviously, this event generate gravitational waves, and those gravitational waves are detected. And interestingly, the gravitational wave has information both about the progenitor objects, means those two black holes that are merging with each other, and the remnant black hole. So we can somehow observe the experiments that nature is doing for us. And similarly, we can compare objects So these mergers and their observational results are detected by the gravitational wave detectors, and we have images of black holes produced by the Event Horizon Telescope, and we can compare these images with each other. So in a sense, it's a kind of manipulation. When, for example, one of them is much more massive than the other, then you can trace the observational effects in your data and find that, for example, if you increase the mass of black hole, what would happen in the experimental results. So okay. Another possible source of support for manipulability comes from analog experiments in which we can manipulate systems that are similar with our with the black hole, but they are not exactly black holes. So, for example, we can intervene in sonic holes or optical analogs. So they are similar to black holes, but there are differences. So because of that, analog experiments have limitations. Their evidential value depends on whether the analog system is really structurally similar to the target system, in this case, black holes themselves. And because of that, they are to some extent questionable. We intervene in the analog system, but that analog is not exactly the same as black holes themselves. So there are questions about this kind of manipulability. And simulations also allow us to model hypothetical scenarios, visual possible interventions, and examine the consequences of changing black holes and to see what will happen if we change something. Somehow computer simulation, I would say, complement the other methods or used in the process that the other kind of manipulations are carried out. And taken together, this provides a form of reason for us that there are different ways for saying that, for claiming that black holes are manipulable. And among them, some of them are stronger than others. For example, natural experiments, I would say, is more convincing. But all of them help us to have some knowledge of how to change, for example, the mass of black hole and see the observational effects. So black holes, at least we have a well-defined notion of what it means to manipulate black holes and to see the effects. So now, beta evidence for black hole. First of all, we should know what does it mean to have empirical access to black holes, because by definition, black holes are nothing can escape from black holes, even when no signal, and the only thing that might escape from them is Hawking radiation, but there's no confirmation for that. But anyway, the point is that they affect the environment, and that environment causally connect to our instruments, and we detect the final chain of that causal relation with our instruments. And in this sense, black holes are empirically accessible. But then to know if the empirical results are reliable, entity realists, for example, here, Nancy Cartwright, and I myself rely on a form of robustness analysis to see if we have different observational channels for the same result and to confirm that that result is reliable. Let us begin with perhaps the most famous case, the Event Horizon Telescope. The Event Horizon Telescope combines radio observatories across the globe into what is effectively an Earth-wise telescope. So there are different features of this telescope all around the globe, and it makes the whole Earth like one telescope. And these are two images of black holes produced by them. And interestingly, in a white paper published by one of working groups of the Event Horizon Telescope collaboration, robustness is understood as a key factor. And the idea is that this collaboration deliberately um, um, take robustness seriously. Their primary concern was to avoid false positives. So that what's important is to not have. It was a kind of conservative approach that the results should be reliable enough. So they changed some factors to have robust evidence, but robustness comes with costs, and this cost is that we might some factors, some really genuine or real factors might be omitted. But that depends on the kind of a strategy that they had, because the strategy was to find something reliable. They tried to employ this kind of conservative approach. And this is quite consistent with the spirit of entity realism, I would say, if there is any spirit for entity realism, because we want to be really sure about something. It's about the empirical result, and then about the existence of entity, and then some properties, and not about the whole theory, the whole theoretical description. And as Dabrowski again and Elder argue, robustness is enhanced in the case of Event Horizon Telescope by variations in the teams involved in imaging, the algorithms used, and the parameter values chosen for algorithm implementation. So there are some changes, different teams that are used, different algorithms that they have used in that detection, and parameter choices. But this is not the strongest argument for the reliability of evidence we have for black holes. Indeed, there are different observational channels. Even Horizon Telescope is just one of the observational channels, which works based on radio telescopes. There are optical telescopes, X-ray telescopes, infrared telescopes, gravitational wave detectors, and as you see, they detect different aspects of black holes, or their behaviors, or the effect of black holes on the environment. So the upshot is these observations reveal different features of black hole behaviors, and more importantly, they rely on at least two distinct physical processes, electromagnetic signals. The first one, radio telescope, optical, X-ray and gamma telescopes, infrared telescope. All of them rely on electromagnetic signals. And this one, LIGO, Virgo, and Cadra, they rely on gravitational wave physics. And these two provide two sort of independent ways of detecting black holes. And now gamma, the third condition. The idea here is that even robust evidence might be accounted for by different hypotheses. So we might have E1, E2, 2En as independent lines of evidence, but still there might be two hypotheses, H1 and H2, both of which can explain all the available evidence. So for this purpose, we need this third condition. And what I would like to emphasize is this form of, I understand this as a kind of societal inquiry, in the sense that it depends on the kind of community that we have in black hole research, in particular here. And here I partly follow Peter Vickers and his discussion on future proof science. The point is that if the relevant society or community, scientific community, is large enough and incorporate a substantial diversity of perspectives, and they discuss the issue, different hypotheses for decades. In the case of black hole, they have discussed the idea and different alternatives for like 5, 6, or more decades in different communities. So this gives us a form of meta-level evidence that perhaps this dominant hypothesis is the only one, but it's a sort of evidence, meta-level evidence for this purpose. And astrophysicists have extensively considered rival explanation, including neutron star. That's an important rival. And as you see in this quote from Eric Curiel, for a long time, some researchers hoped that extremely compact objects could be explained without invoking black holes, for example, neutron stars, but then more and more doubters were won. As this, other models couldn't account for the same empirical evidence. But here, there's an important point that in the kind of eliminative reasoning that people in scientific communities use, they rely on GR model simulations and a lot of theoretical work. And that's a part of Alza's argument, to argue that entity realists cannot be entity realists. They should become some sort of theory realist, because they use theories, they use models, they use GR in particular. But first of all, I think a kind of response to this is that entity realists are not against using theories or models, but they have considerations, particular considerations in using theories and models. Or for example, for Cartwright, we can use models and theories to infer, but the point is that the model that we can use should not be the only model. It should be good enough, and then we should be able to change it with another model. So we should have this freedom. We should not rely only on one particular model. So anti-realism about models or non-realism about models that Cartwright has doesn't mean not using models in inferences. They could be good enough, but they should be exchangeable with other models. And for hacking, the main issue is vicious circularity. And I delve into this idea now. We should know more about his account of observation. And so we can use theories. Theory ladenness is quite fine, and there's no objection to that. But the point is that the observation that we have should not rely on the theory that we want to confer it, or something like that. So just, Hacking's account of observation. So Hacking follows Chaper's account of observation, and this is telling us, on this view, something count as observing rather than inferring, when it satisfies Chaper's minimal criteria. And when the boundaries of theories upon which it relies are not intertwined with the facts about the subject matter under investigation. And these two are Chaper's conditions. Information is received by an appropriate receptor. Okay, let's see from that side. And second, that information is transmitted directly to the receptor without any interference. And Hacking adds that there shouldn't be any vicious circularity. That's also important for him. So that's the main concern. And thanks to this unity of science, so science is not, there's no unity in science. It's part of science, theoretical science, that our observation relies on that. But then there's another part of science that is disunited from this part, and we want to confer that. Thanks to this unity of science, we can have observation. So the main point for him is this kind of theory ladenness. So this observation suggests a different way of reading Hacking's famous discussion of extragalactic entities. Extragalactic means entities that are outside of our galaxy, so they are very far. The standard interpretation focuses almost exclusively on the absence of manipulation. But what I want to suggest here is that I think two additional factors are really important. First, observational evidence available in 80s when Hacking argued for anti-realism was much weaker than the evidence available today. And more importantly, the available evidence was heavily dependent on theoretical assumptions in ways that Hacking regarded as problematic. So with this in mind, I want to reconstruct Hacking's argument. It would be something like that. It's an argument for anti-realism about extragalactic entities. Let's call them EEs, or astrophysical entities that are very far from us. EEs have not been manipulated, or they are not manipulable at all. The theories upon which the alleged observations of EEs are intertwined with the theories about the EEs. So, because of these EEs have not been observed, we remember that for Hacking, This is one important condition, but when it is not satisfied, we cannot say that there's observation. So we do not have observation in observation of extragalactic entities. So these have not been neither manipulated nor observed, and therefore there's neither experimental or observational ground for a realistic count of EEs. This argument can be challenged at 2 points. Regarding the first premise, recent work on entity realism suggests that we do not need actual manipulation. Also, regarding the second premise, and I want to highlight this, the crucial question becomes whether contemporary black hole science has developed strategies to mitigate the kind of circularity that existed decades ago. In Hacking's case study of one of these extragalactic entities, namely gravitational lenses. Thanks to a very recent paper by, again, Dawozeski and Elder, published in 2025, it sounds that now we have strategies. So their work suggests that there are strategies to mitigate this problematic situation. They explain the problematic situation. It's more or less similar to the problem Hacking raised about vicious circularity. And there are strategies to mitigate that circularity. And in two of them, at least, we can find that relaxing GR assumptions is possible. So we can infer from the empirical evidence the cause, in this case, the existence of black holes. And we can rely on GR and other models, but it should be possible to relax that model, to use alternative models. And there are strategies to do so. So the final part, conclusion, entity realism about black holes. So I have argued that realism about black holes is possible within an entity realist framework. At the same time, this does not lead to a kind of comprehensive or out-and-out realism about all theoretical theories about black holes. There are some considerations or reasons for cautious. The first one is more exotic mathematical models of black holes, which make possible, for example, time-like curves, which means that we can travel to the past, or information might lost according to the black hole information paradox, according to some theoretical understanding of black hole. But more importantly, because of the plurality of different notions of black holes, as I mentioned earlier, and Eric Kuhlmann argues convincingly, there are different theoretical conceptions of black holes, and they are not compatible sometimes with each other. Different subfields of physics, they use different definitions, and we cannot say which one is exactly the ultimate definition of black hole. So we should be more cautious about all of them, can use them more pragmatically, but at the same time, we can be realist about the existence and properties like mass of black holes. So entity realism provides the construction of current scientific knowledge of black holes. It captures the justification astrophysicists have about the existence and certain properties of black holes. It's cautious about those aspects that there's no consensus about them within the community of physicists, and about that an entity realist is non-realist. And yeah, thank you for your attention.